Hello, and welcome to a chemistry video tutorial on C5 of the energy option. This chapter is environmental impact of global warming. So I've split this up into 6 different central topics that we need to learn in order to understand C5, and these are the greenhouse effect, the sources of different greenhouse gases, the greenhouse factor, projections and effects of global warming and the greenhouse effect, ocean acidification, and global dimming. So one thing that should be noted about this chapter in specific is that it's very conceptual and very explanation based. So when you get asked questions that are based around the topics that we're going to cover on an IB exam, you will not get any questions that deal with numbers or calculations, but rather explanations. So let's get started with the greenhouse effect. So before understanding what the greenhouse effect is and how it works, we need to look at temperature here on Earth. This is a bit of a misshapen Earth, but it'll have to do for this tutorial. So on Earth, we receive energy from different sources, and we also give energy out. And this is what is called a steady state balance of energy. And it's the reason why we're never always heating up or we're never always getting colder. So the biggest source of energy here on Earth is the sun, and the sun gives off what is called solar radiation, and this will come and sort of hit the Earth like that, right, in rays. Now, solar radiation is in the UV spectrum and also the visible spectrum. Those are the two sort of ranges of wavelength of the light that we receive from the sun. So when this solar radiation comes in, multiple things happen. It doesn't just hit us, right? This layer over here that is labeled the atmosphere will actually deflect some of it as it comes out. So a little bit of the solar radiation is deflected and gets sent out back into space. And some of the gases in the atmosphere will actually absorb this. And so it'll be dispersed and sort of absorbed by different gases over here in the atmosphere. But most of the solar radiation will actually hit the terran surface of the Earth and sort of heat things up. And that's the reason why when you're standing outside in the sun, you can feel warm, because most of the solar radiation that you are receiving is hitting the Earth. And as I said, some is getting dispersed back into space. And so once this happens and the Earth is heating up, well, now is when we need to consider the other side of the steady state balance, right? Because right now we only have energy going in, but we're missing the energy going out. So how does energy go out? Well, the Earth will actually radiate, after a while, some of the solar radiation that is absorbed, right, and that hits the surface. It will radiate it out, but it will do so at slightly different frequencies and wavelength. So I previously mentioned that solar radiation is ultraviolet and visible in the spectrum of light. Well, when the Earth radiates energy that is already absorbed, it will actually do so in a longer wavelength, and it'll be infrared. So this is what's called IR radiation. So now that we know what the steady state balance of energy is, we can actually look at the effects of this over here, because this expulsion of infrared radiation is actually what triggers what is called the greenhouse effect. So in the atmosphere, there are multiple different gases. Amongst these, CO2, H2O, in gaseous form, right? And these gases all have covalent bonds. Now, something that you need to know about covalent bonds for this unit is that they all have a natural frequency. Now, what this means is, and we can take, water, for instance, and we draw it out here. These covalent bonds will have a natural frequency, which means that at a certain frequency, they will begin to vibrate. Now, what happens is, we can take this bond and we can enlarge it here so that it's easier to see. The frequency of the emitted infrared radiation can actually match the natural frequency of some of these covalent bonds. And so what this does is it causes the bonds to start vibrating. And they vibrate, pretty aggressively. And when they do this, they actually heat up the air around them. And so when you have this infrared radiation going up, some of it is, causing these bonds to sort of start vibrating, and that heats up the air around the area where this ray is getting emitted, and some of this heat will radiate off into space as well. But the problem here is that some of it will stay in the atmosphere, and this will keep happening with the continuous expulsion of infrared radiation. And so the problem here is it greatly delays the speed at which energy is expelled. And so what you end up having is a greater rate of energy coming in than you do a greater rate of energy going out. And so that will naturally increase the temperature here on Earth. And that is why the greenhouse effect is linked to global warming. One last thing to note about the greenhouse effect, and you don't need to know this for the IB, but it's interesting to know nonetheless, is the reason why it's named the greenhouse effect, right, of all things. Well, you may or may not know that a greenhouse is sort of a facility or a structure where plants can grow, and because of that, they typically have roofs and walls made of glass. And it is actually very humid and very hot inside greenhouses sometimes if they don't have proper ventilation systems, because what happens is the glass material will allow heat to get in the form of light, but it will actually trap it inside and it won't allow it to go out again. This will not happen. And so it is analogous to sort of the system of different energy interactions that occur in the Earth's atmosphere. So that's all you need to know about the greenhouse effect for the IB. Playing that video back, I realized I may have sounded a bit too condescending, so I apologize for that. But moving on to the sources of greenhouse gases, there are two that you need to know for the IB. Two greenhouse gases that you need to be aware of, which each have multiple sources. And these are water, which is displayed on the left, and carbon dioxide, which is displayed on the right. So for carbon dioxide, many of you have probably heard of it, contributing to global warming. It's mainly created and dispersed into the atmosphere by the burning of fossil fuels. And as far as water goes, well, the sources for water are oceans, seas, lakes, rivers, and all of that. Now, in this slide, I've also included methane gas because it's also a relatively abundant greenhouse gas that, it's good to be aware of. And it actually comes in large part from livestock. And that's why, you might hear people say that moving to vegetarian or vegan diets can actually be beneficial to the environment for multiple reasons. Well, the production of methane gas is one of them. Now, it may be surprising to hear that H2O is actually the most abundant greenhouse gas. And it may be surprising because it's usually not included in graphs and figures that deal with global warming. Now, the reason for that is when we talk about global warming, we're talking about the human-caused aspect of it, right? It's a problem because we have contributed to it, and now it's getting out of hand. And so we don't consider H2O as sort of too much of a factor in that, because H2O has always been around and it's always been a factor for global warming. And it's always been a greenhouse gas. So there's nothing we can do to sort of mitigate the effects of, water becoming steam and then contributing to the greenhouse effect, which we just looked at. Now the problem is actually carbon dioxide, and that's because carbon dioxide is produced by burning fossil fuels, which is something that we humans do. And so because of the Industrial Revolution, the world now requires more fuels, more energy, which means that more CO2 is produced every year. And, over the past modern history, or recent history, CO2 levels have increased by a lot, and that's what is causing a lot of the big issue with global warming. Now, it's estimated that CO2 actually contributes about 50% to global warming, so it is a real problem. Now we're going to look at something called the greenhouse factor to get a better understanding of how these things are measured and how we know exactly how much each gas contributes to global warming. So not all gases are equally efficient at absorbing infrared radiation. The ability to absorb infrared radiation actually depends on the change in dipole moment that occurs as a molecule vibrates. And so, depending on the gas, it will be more or less effective at absorbing infrared radiation, meaning that some gases contribute more to global warming than others do. So, for example, symmetric nonpolar diatomic molecules such as nitrogen or oxygen in their diatomic form are actually not considered greenhouse gases because they don't have the ability to absorb infrared radiation. However, the ones that are displayed on the screen right now, which are methane, CO2, and water, actually are. And so we need to find a way to quantify how able they are at absorbing infrared radiation. So what humans decided to do was come up with a relative value scale, which assigned numbers called greenhouse factors based off of the gas's ability relative to carbon dioxide's ability. And that's why the greenhouse factor for carbon dioxide is 1, and then the greenhouse factors for all other gases are assigned relative to carbon dioxide. It uses carbon dioxide as a reference point. So for example, water, H2O, has a greenhouse factor of 0.1, and methane, CH4, has a greenhouse factor of 30. So one way to better understand the scale is by imagining how many molecules of one gas might be needed to match another gas in terms of the ability to absorb infrared radiation. And we can do that just looking off the numbers. So for example, methane has a greenhouse factor of 30, CO2 has a greenhouse factor of 1. So what that means is that in terms of equal ability to absorb infrared radiation, 30 molecules of CO2 equal only 1 molecule of methane. Methane is much more capable and much more able to absorb infrared radiation than CO2 is at a per molecule level. So what actually are the effects of global warming, and what are some projections that people have put forth? Well, many experts are saying that CO2 levels might actually double in the next 100 years if CO2 emission levels currently do not drop down drastically in the near future. And if CO2 levels actually double in 100 years, there are many negative effects that would affect sort of the way we live in our world today. And some of these effects are changes to agriculture. Farmers might experience lower or changed crop yields as a result of the effects of global warming. Things like sporadic weather are already being experienced and are having a direct impact on agriculture. We might see cases of biodistribution where, for example, the loss of cold water fish habitats could lead to fish species going extinct or moving to different areas, making it very hard for us to continue fishing in the areas that we do or continue fishing at all. A third effect is rising sea levels. We've all heard about this one. The thermal expansion and the melting of polar ice caps and glaciers is actually causing the average sea level to rise, meaning that coastal cities, such as Venice, for example, are at a high risk of being submerged if nothing is done, at least to some extent. So it is time for people to wake up and actually do something about this. And the UN has put forth the SDG goals, which are outlined, so basically different outlines for pressing problems, and a few of them have to do with global warming because it's a real issue that we need to stop contributing to. Now we're going to look at something called ocean acidification. And it's pretty self-explanatory. You can guess from the name that it means that oceans are becoming more acidic because of global warming. So in order to understand this, the first thing that we need to look at is what happens to the CO2 that is actually produced by the burning of fossil fuels. Well, it turns out that about half of it is absorbed by the ocean. It gets dissolved into the oceans, or it gets absorbed by plants during photosynthesis. And so The first equation here in the slide is an equilibrium reaction that deals with gaseous carbon dioxide and aqueous carbon dioxide that can be found dissolved in oceans. And so the following system of equations you need to memorize for the IB, but if you understand them conceptually, then they shouldn't be too much of a hassle. So starting with the second equation, we have the aqueous carbon dioxide, which reacts with the water, which is surrounding it in this case because it's already dissolved in the ocean, to create carbonic acid. And now I think you can guess why the ocean becomes more acidic, because this carbonic acid can actually react to form hydrogen carbonates or carbonates, and it dissociates to release these H plus ions that are released into the ocean and hence make the huge bodies of water of our world more acidic. Now, this has a lot of effects on marine wildlife, which indirectly affects us because we eat marine wildlife, and so this is a problem not only for fish but also for humans. In fact, over the past 300 million years, oceans have actually been slightly basic, pH levels averaging about 8.2, and yet today the pH has decreased to around 8.1. This doesn't seem like too big of a change, but remember that the pH scale is actually logarithmic, and this will continue to happen. It's not a one-time change. And so this drop of 0.1 actually represents a 25% increase in acidity. So if levels of carbon dioxide actually continue to increase at this rate, then the pH of oceans could fall further, which would affect shell-forming animals, because it affects the materials inside shells. And this would affect corals, it would affect oysters, shrimp, and even lobster, which are all things that indirectly affect us. The last thing that we need to look at for Chapter 5 of the energy option is something called global dimming. Now, let's take a look at the graph over on the right side of the screen. This plots the global average temperature of recorded here on Earth over time between 1850 and 2050, although projections are not shown. So we can see that the general trend is an increase relationship, but it still seems pretty sporadic. We see it go up and down and up and down and up and down, and although overall it is increasing, somebody can question why it's so sporadic in the first place. Well, scientists believe that this has to do with something called global dimming. Global dimming is the phenomenon where particulate matter that is formed by incomplete combustion, so this can be anything from soot to ash to different sulfur compounds, actually contaminate clouds. So over on the left, for example, we have a picture here from Mary Poppins. So we have a chimney sweep, and on his face he has soot. And soot is an example of something that is formed from incomplete combustion, and that sticks on things very easily, and it flies around and can pollute clouds, for example. And so when these pollutants actually pollute clouds, they make these clouds more reflective of incident sunlight, meaning that more solar radiation is reflected back into space, which we saw in the greenhouse effect video at the start of this tutorial. And so global temperatures are actually lowered or do not increase as quickly. And so this is something that it's called global dimming, and we have to take into consideration when we consider data for global average temperatures. If we look over here on the right, and you look at the 1960s, you will see a sharp drop in global temperature. And that's because there was a lot of volcanic activity in the 1960s that actually led to a lot of particulate matter entering the atmosphere and polluting clouds. And so more sunlight was reflected back into space. One thing to note about particulate matter and global dimming is that if less particulate matter were to enter the atmosphere, it is very possible that the effects of global warming would be heightened, because to some extent the polluted clouds can actually serve as a shield to incident sunlight and let less of it actually penetrate the atmosphere and hit our surface. To conclude, CO2 emissions are a problem at the current state that they are at, but certain measures can be taken in order to mitigate their effects on global warming, and the IB can ask you about these strategies, so make sure to pay attention. So the first is increased energy efficiency, simply using less energy than we currently do, and this is where things like turning off lights when you're not using them comes in. If we use less energy, then we'll pollute less when making the energy. The second strategy is reduce dependence on carbon-based energy resources. So instead of burning coal for energy, we could resort to building more nuclear power plants and using nuclear energy, or building wind turbines or hydroelectric plants, and just living off of more renewable sources of energy. And the third strategy is actually the capture and storage of carbon from fossil fuels or from the atmosphere. So there's a lot of carbon currently in the atmosphere because of all the fossil fuel burning that we've been doing thus far. One strategy would be to sort of take it out of the atmosphere. There are ways to do that with current technology, and then we could put that carbon to use by, giving it to plants or doing things along those lines. So that concludes Chapter C.5 of the option for energy. This goes for IB Chemistry SL as well as it does IB Chemistry HL. As I said, there are no sort of number-based or calculation-based problems that I can show because they simply don't exist. If you are quizzed or asked or tested on this unit, it will be always explanation-based. So make sure you get a strong conceptual understanding of how all the factors and all the concepts work so that you can come up with any explanation that they could possibly ask you for. Alright, I hope this tutorial was helpful, and see you next time if I do end up making another chemistry video tutorial.